Okay, I'm recording. Okay. So welcome everyone to this new Graviticulous seminar of this Thursday. Today is the turn of Álvaro Santos. So Álvaro, many thanks for giving this talk. Álvaro got his bachelor degree in physics in 2018 in Universidad Federal da Bahia. And his master's in 2020 from Universidad Federal do Rio Grande do Norte, UFRN, sorry. And he is a PhD student since 2020 and a member of the Particle and Astroparticles group from the International Institute of Physics, UFRN, since 2018 as well. So Álvaro, please go ahead and start your talk.
Okay, well, thanks for the very nice introduction. And I'd like to thank as well for the opportunity to present my work here. So, beginning, today I'm going to talk about a paper that we did last year, which is themed Vectorlike leptons and inert scalar triplet, lepton flavor violation, G-2 and collider searches. So, first of all, I would like to give you guys a very idea of the goal of this paper, because I feel like it's very important to show you guys the goal of the paper then in order to understand the timeline of the whole work. So the main goal of this paper was to provide a solution to the G-2 of the muon. That was the main goal. So, however, we have dealt with a model earlier where we have this model which was really nice. It could be used for many different things, but this model could not explain the G-2 of the muon. So we pick this model, which we know it's very good, and then we make some extension to this model. And in order to explain the G-2 of the mu, so that we can explain many other things with the G-2 of the mu at the same time. So, however, in order to explain the G-2 of the mu, this model that we consider as a baseline, it has some limits, specifically limits coming from collider searches. And these limits, they are quite strong. And because of that, we need to consider again the limits from collider searches. And in order to refine our model, we made this choice to also consider lepton flavor violation as another source of bounds for our model. So let's begin. Here is a summary of this presentation, where first I'm going to give a very brief introduction to a few topics, such as the G-2 of the muon, lepton flavor violation, and 331 models, which are the baseline model that we are considering here. And then I'm going to talk about the simplified models that we use to extend the 331 models, which was the case of an inert scalar triplet and an inert scalar with exotic leptons. And then in the sequence, we're going to talk about the results. I'm going to show you guys some plots that we found in the paper, and I'm going to conclude the presentation. So, this, as I said, this paper was produced last year and it is already published in PRD. And this work was a collaboration between myself and my advisor, Farinaldo Queiroz. And we also have the presence of Professor Kovalenko from Universidad Andrés Bello in Chile as well. And we also have the collaboration of Professor Sinha from University of Oklahoma. And we had a colleague of ours, Clarissa Siqueira, which at the moment she was a postdoc in our group. She's still a member of our group, but she's no longer a postdoc at the International Institute of Physics. So, what is the mu G-2? Especially this year, this became a very hot topic, since there was the results coming from Fermilab was published at April, and it became a very hot topic with many papers on the subject. And basically, I'm going to try to give a very brief introduction why this is a problem. So the first thing that you need to know about the G-2 of the muon is that there is a prediction coming from the Dirac equation. And the Dirac equation predicts that G, which is the gyromagnetic ratio, it's equal to 2. However, we know from quantum theory that there are many kind of contributions to the magnetic moment of particles. In this prediction of G equal to 2 is only valid at 3 level. When you consider the contributions coming from loop diagrams, there are many different contributions that make that this G value starts to deviate from 2. And so in order to see how much this deviation it is, there are usually this parameterization here is usually done. And what is this contribution coming from loop diagrams? In the case of the standard model, we have here these 4 different contributions. The first one is a contribution coming from electromagnetism, where you have this diagram here, which is mediated by a photon. Then you have the second and third diagrams here, which are the contributions from the weak sector, which are mediated by the Z and the W bosons. And then you have this last contribution here, which is the most problematic of them all, because as you can see, it happens at 2 loop level, and it's very difficult to calculate this contribution because quarks are very problematic, especially because the G-2 of the muon is a low energy phenomenon. And in this case, there happens a phenomenon known as hadronization. So this means that the calculation of this last contribution is very tough to do. And actually, it is the most, it's the biggest source of error in this kind of calculation. It is so big that there are some collaborations that think that perhaps the G-2 of the muon is not a problem. It is only a question of the hadronic contribution not being calculated right. There are some people that believe in that. So, going on. Here, the reason why the G-2 of the muon is a very important some time. And here, this is how we measure this difference, where we consider the experimental value, because you can measure the G of the muon, you can measure in experiments such as Fermilab. And here I have a small picture of the Fermilab experiment, G-2. And then you compare this experimental value with the predictions from the standard model. And then you see that there is a discrepancy here. And as you can see, this discrepancy is pretty small, not the 10 to the minus 11. It's a really small discrepancy. However, this discrepancy has been seen since, well, here I'm considering since 2009. And then the discrepancy keeps on living. Many other experiments from different places, they still see this discrepancy. So this is a clue that perhaps there is something going on with the muons that we don't know what it is. And then this can show that perhaps we have some new physics related to the discrepancy on the G-2 of the muon. And here we have the latest result from Fermilab, which was published this year, where they found a discrepancy of 4.2 sigma, which is a pretty strong discrepancy. However, as I said, there are some people that believe that perhaps this discrepancy is just a case of we don't knowing how to calculate the hadronic contributions. But to be honest, I believe that it's just a matter of time. Perhaps when we get more precise experimental measurements and more precise theoretical calculations, we will be able to see a new discovery, which is in the 5 sigma region. So, going on. The second topic that we consider in this paper was lepton flavor violation. And what is lepton flavor violation? Lepton flavor violation basically means that you have a process that at the beginning of the process, you begin with a lepton of a specific family or flavor, which are basically the same thing. And then at the end of the process, you have a lepton from a different family. So this lepton flavor was not conserved in the process. There are many kinds of processes like that. And however, in the standard model, lepton flavor is a global symmetry, or as people say, an accidental symmetry, because it does not come from a gauge group. So it is just a symmetry that we happen to see in the process, but there is no meaningful reason for us to believe that this is a symmetry of nature. So we believe that this is just a coincidence, and this symmetry can be broken at any time. And so there are many different experiments that deal with lepton flavor violation. However, in this paper, we consider the very specific muon decay The reason why we chose the muon is because the muon has the most strong constraint. So if our model survives the limits comes from the muon, it will survive all the other ones. And specifically, the process that we chose was the decay muon to E gamma, which is the process where a muon decays into an electron and a photon. And as you can see here, the branching ratio of this process is really small, in order to 10 to the minus 13. So this is a very rare process. And here, as just in the case of the G-2 of the mu, I brought a quite brief history of the measurements with charge lepton flavor violation. And as you can see, the precision of these measurements is getting pretty high. Since in the last 70 years, it got pretty high precision. So this means that lepton flavor violation, it's a very strong bound in models that can perhaps have some processes like that. So we thought that this was a very nice candidate of benchmark to be used to see whether our model was good or not. But let's go into the baseline model. Sorry. So 331 models, they are basically a class of models. When I say a class of models, I mean that there are many different models that can be used with the same structure. And what is the structure of the 331 models? Well, basically we get the electroweak sector of the standard model, and we make an extension in the gauge group. And this extension is represented here, where we go from SU2U1 to a SU3U1 gauge symmetry. So considering now the gauge symmetry of the color, now we have a gauge structure of SU3, SU3U1. So that's where the name of this class of models comes from. However, since the fermions need to be represented in the fundamental or anti-fundamental representation of this gauge group, now our fermions needs to be represented as triplets. As you can see here, here is the case of the leptons, for example, where you can see the first and the second component as just the same as the standard model, the same components with a neutrino and a charged lepton. However, we now have a third component. And this third component can be, there are many possible options of this third component. And each of these different options represents a different model. Here in the case, I'm showing the case of a model called a heavy neutral lepton, where this third component here represents basically a very heavy neutrino, for example. If you want to have a very heavy neutrino, and this particle can be used, for example, as a candidate of dark matter, in your model, for example. So this is a very versatile model in that sense, because I'm going to show later a few of the topics that this model is being used in the literature. But this is a very versatile model because of that. You have many different options that you can use for many different problems of interest. And the same thing also happens with the quarks, because just in the case of the leptons, the first two components is the same of the standard model. However, you have a third component for the quarks. And then this third component, you can call an exotic quark, for example, can be used to solve some problems in like hadronic physics, for example, some kind of fluctuation that people usually find in experiments. So it's a pretty nice model. And another very interesting thing is that since we are extending the gauge group, we now have 5 new degrees of freedom, which basically mean 5 new gauge bosons. And these new gauge bosons, they suffer from limits from colliders. And that's the main reason why we are considering colliders here. Because since we have these limits coming from colliders to the mass of these gauge bosons, we can put some limits constraints in our model. And that's the main reason why we're considering collider searches. However, the extension does not just stay with the fermionic sector. The scalar sector is also extended because we have all of these new particles, and these new particles needs to get its mass from somewhere. And so this means that we need to have some more scalar particles. And here is the case of that model specific that I just said, which is the heavy neutral lepton. So we have three different scalar triplets. However, you can produce masses for the particles with just two of them, which is another model called economical 331 model. And in this case, one of these three triplets, it needs to get a vacuum expectation value. Why? Because we know the standard model works fine in its energy region. So we need to go back to the standard model at some point. Sorry,
Álvaro, Victor has a question.
Yes.
Oh, okay, you can ask.
So I was wondering about if there are different symmetry breaking patterns that you have in this model, because at the end you have to end up with electromagnetism and color,
Yes.
right? But can you comment on that?
Yes, in this presentation, I didn't put this part, but the pattern of symmetry breaking is just like this. First, you come from this 331 symmetry, and then usually this guy, he develops a vacuum expectation value. So you go back to the standard model, and the other two triplets there, they develop a vacuum expectation value. So the combination of those two, they kind of are the same of the Higgs doublet. So they get a vacuum expectation value, and then the sum of the two different vacuum expectation value needs to be the same of the Higgs. Otherwise, you won't have the same results that we have with the standard model. So it's basically this chain of symmetry breaking: 331, 32, 331. Then one of the triplets gets a VAV. Then you go back to the standard model, and then the other two triplets get a VAV, and then you go to electromagnetism. That's the pattern. Did I ask your question? Did I answer?
Yeah. Thank you.
Oh, thanks. So, going on. As I said, this kind of model is very appealing because since we have many different options to be used in this model, you can work with many different topics, such as dark matter, as I said at the beginning, neutrino masses, because you can add another scalar, for example, triplet, but now a sextet triplet, which will be responsible to produce neutrino masses, which is also a part of another 331 model, which is called minimal. And then you can also solve problems in flavor physics because of these new quarks there, and collider physics. However, there is a problem with these models. And the problem is that they cannot explain the G-2 anomaly whatsoever. And the reason for that is that because the scale of symmetry breaking, which is basically V chi, it is related to the mass of these new gauge bosons. And we know that LHC has been searching for these new gauge bosons for quite some time, and they haven't seen anything up to now. So these sliders, they also put a limit on the scale of symmetry breaking of the model. And we did our work last year as well on the implications of the the G-2 of the muon for this kind of model. And we consider 5 different models. And in all of those models, they were not able to explain the G-2 anomaly. And the reason for that was because since we have these limits on the scale of symmetry breaking, basically what would happen? The region of these models that were able to explain the G-2 of the muon needed to have a very small scale symmetry breaking. However, the limits from Collider, they put a very strong limit on the scale of symmetry breaking, which was way higher than what was necessary to explain G-2. So this whole region was excluded. So we basically were not able to explain the G-2 in this framework. So that's where this paper came from, because we know that it's a very interesting model, but it cannot explain the G-2 of the muon. So we thought, well, perhaps we can do some small extensions of the model that were able to explain the G-2 of the muon. And just to show you guys the colliders, why the colliders limits are so strong, is because since these new particles, they get massive at the moment that chi develops a VAV, all of its masses depends on V chi. So and which is the main contribution because Vk is way larger than V rho and V eta. So there is a very strong relationship between the mass of these new gauge bosons and Vk. So the limits from LHC, they are measured, they are in the masses of the particles. So we can, in this case, infer a limit on Vk. And the same happened for Z prime or W prime, or also adjacent X, because we have 5 new degrees of freedom, so we can have 5 new different gauge bosons. So we have this freedom to choose which one of them has the better limit. And the choice that we found was that the Z prime has the better limits, because the limits from LHC to a Z prime were the strongest. So if our model survived the limits to the Z prime, it will survive from all the others. So we chose to use the Z prime as our main benchmark in order to study our model. And these were the limits that we consider in this paper. And, well, this limit here depends on the fact of depends on the decay width of the Z prime. And so we consider the case where the Z prime could decay into leptons and into all these new exotic particles. So this limit is a bit weaker than the limit from LHC, which was another 4 TeV, if I'm not wrong, 4 TeV, which means a limit, way higher limit here. However, as I'm going to show you guys in just in a moment, our model has a lot of free parameters. So we could consider the limits from 4 TeV, which I believe it was going to be 11 TeV for the scale of symmetry breaking. But since our model has so many free parameters, we can adjust our model in order to fix this limit. So we consider this more conservative limit, and we did our calculations with that. And another very interesting thing that we did in this paper was we consider how would be the projection of our model in the case of high luminosity LHC and high energy LHC, which are the upgrades which were already being done, I believe, for the LHC. And then we found that these limits were put the scale of symmetry break to a higher region if this new gauge boson was not seen at these 2 upgrades. And then we consider these 2 regions as a reference for a model in order to see whether we can perhaps induce a sign in those 2 upgrades of LHC. And the way that we did that was by using the collider reach tool, which is here, the website, where you can do this kind of projection, okay? So we're now going to talk about the simplified models that we use to extend the 3-3-1 models. Oh, hi.
Sorry, can I ask you something?
Yeah, sure.
Can you back 2 slides, please? Yes, there. So you have the Z prime. I see here 3 bosons, 3 new bosons. Where are the other 2?
Well, actually here it's 4 because you have W plus, W minus.
Okay.
And then this X boson here, in the case of the model, it is the same boson. However, we have the chi and the chi asterisk, which is they are basically the same. They are different bosons, but they have the same properties.
Okay.
So these represent all 5 of them.
And in your model, you don't have leptoquarks?
No, we didn't consider this, but there are some papers where people consider this case. But in this case, since we are trying to have a simplified approach, we didn't consider this.
Okay. And what could be the difference in those scenarios in which you get leptoquarks? It is in the scalar sector content that makes the difference, or?
Well, to be honest, I don't know, because we didn't go that far into the case of leptoquarks, but I believe that this could have some very interesting consequences, because the quark sector is also extended. So perhaps some of that 3rd quark component, you can think of a leptoquark with that and do some very interesting things. But to be honest, I don't know. I'm not sure about that.
Thank you.
No problem. So going back to the simplified models. The first one was a very simple, actually the simplest extension that we can think, which was the case where we add an inert scalar triplet. Here with inert, what we mean was that we have a scalar triplet, which does not develop a vacuum expectation value. So it does not contribute to lepton, to fermion masses, and not even to the masses of the gauge bosons. It's just a scalar triplet that can interact with the particles of the model. And specifically here, we consider this Lagrangian, which is a simplified Lagrangian, where this scalar triplet only interact with the leptons. We can force that by doing some Z2 symmetry. We can enforce that in the model. So we consider the simplified model in order to see how, if this was a good fit to the G-2 problem. And it's very important here to see that we have a free parameter here, which are the Yukawa couplings. I'm sorry, can you see my mouse? Okay, I was just messing around with it.
No, yes, we can. Don't worry.
Sure, thanks. So with these Yukawa couplings here, there are three parameters. They only are limited by unitarity limits. So they can be pretty high and they can be pretty small. And one assumption the only assumption that we did with the Yukawa parameters was that since this interaction can happen between fermions of different families, and that's the reason why we are considering lepton violation, the only assumption that we did was, well, the Yukawa couplings from the diagonal matrix they are larger than the Yukawa couplings from the non-diagonal regions, which are pretty reasonable assumption, because our main goal here is to explain G-2 of the muon, and we know the lepton violation puts some very strong bounds. They are very strong, put some very strong bounds on the couplings, as I'm going to show you in just a moment. So if we say that they have the same value, the same order of the diagonal, this would just mean that we have a bigger region of a model that would be excluded. So it doesn't make sense to keep it the non-diagonal Yukawa couplings with this at the same order of the diagonal ones. And another interesting thing is that this guy here, phi, he has a interaction term in the potential, scalar potential, which goes like this. So basically what this means is that the phi gets its mass from the symmetry breaking of 331 to 321. So its mass is proportional to the scale symmetry breaking as well. So we can use the limit that we found from colliders to the gauge bosons to study this new simplified model. We can just translate this limit here. It's pretty nice because we don't need to have another different parameter to our model. So just in order to be clear here, we have, in this case, we have three free parameters. The first one being the Yukawa couplings. The second one, this lambda here, which is the relationship between the mass of phi and the scalar symmetry breaking, and the scalar symmetry breaking, which is another free parameter. So the second model that we consider was the case where we have just an inert scalar. It's not a triplet, it's just an inert scalar, and an exotic lepton. Well, actually three different exotic leptons. And so we consider just as the same case, this Lagrangian here, which is a simplified Lagrangian, where they only interact with the leptons. And just as the previous case, it interacts with different families of leptons as well. And as you can see here, we still have the Yukawa parameters. So this is basically the same model of the last one, because the contributions to the G-2 and to the branching ratio, they only depends on the kind of particles, which in this case would be a scalar. So we will use the same contributions, with the only difference here being that the fact that we have a fourth free parameter now, which is the mass of this exotic lepton. And the reason why this is a free parameter is the fact that this exotic lepton needs to be vector-like. And the reason for that is the fact that since we are adding a new lepton to our model, this can perhaps cause some anomalies in our model, and we don't want that. A model with anomaly is not good news. So this means that this lepton needs to be vector-like in the sense that its gauge couplings, its couplings with its left-handed component needs to be the same with the right-handed component. So even though we consider these leptons in the anomaly calculations, they will cancel each other. So that's not a problem. However, there is the simpler case where we consider that this guy here is just a singlet over the symmetry, which is a simpler case, so we won't have any kind of anomaly at all. So, but how these guys contribute to the G-2? The main equation for the contribution is given by this equation here, which is considerably big equation. And then where we have this integral of this parameter here, which is the Yukawa coupling. So we see that there is a clear dependence on the Yukawa couplings, and there is also the dependence on this epsilon b value here, which is basically the ratio between the mass of the particle, which is inside of the loop besides the scalar, and the mass of the muon. So in those two cases here, which is represented by those two diagrams, the first diagram here on the left is the diagram of the second case, which is the case with the exotic lepton. So the exotic lepton is here inside of the loop. So epsilon b will be me over mu. And in the second case, which is just the case of the inert scalar, this epsilon will be 1 because the muon is inside of the loop. So that's the main difference between the two contributions, okay? So, but how does this model contribute to lepton flavor violation? The main contribution.
Álvaro, sorry, can I ask you, interrupt you again? The previous slide, please. Yes. So in the second diagram, what is the term that allows you to have this inert coupling with two muons at the same time?
No, actually, it only interacts once. But since this is a loop diagram, you have the first interaction here in this vertex, and then this muon, which is here, it produces a photon and then interacts back. So this is two different interactions.
Yes, but for instance, if you have a vector-like fermion, I mean, how is the term that produces that interaction between the inert scalar and the muons fields? Because you cannot have a singlet scalar with a right-handed muon and doublet or triplet SU2
Oh, right,
or
right.
SU3.
Now I understood your question. Well, let me go back here to the model. This F guy here, it is a triplet. So this is also
yes. Okay.
I forgot to say that.
Yeah. So the second diagram corresponds to this model.
Yes, this guy here.
Okay. I see. And just maybe a silly question: why do you call it inert?
It's because it doesn't develop a VEV, so it does not contribute to the masses of the particles.
Okay. Perfect. Thanks.
No problem. So here we have the contribution of these two particles to the branching ratio of the decay muon to gamma. And as you can see here, there is dependence on alpha and the Fermi constant, but there is also this form factor A, which is represented here. And as you can see, there is also the dependence on the Yukawa couplings here. And this I++ here is basically the loop integral, where you have this integral where dependence with the masses and that's textbook here. So the results, which is the most important part. These are the results that we found for the case of an inert scalar triplet. So let me first explain what this plot is, so you can understand the results that I'm going to talk. So This is a plot of the value of delta A mu as a function of V chi, which is the scale symmetry break, which in the end is our main parameter here. So we have these horizontal lines. These green lines here represents the region between the arrow bars of the value of the G minus 2 of the anomaly, the G minus 2 of the muon. Just to be clear, since this paper was from last year, we did not consider the values that were published this year. However, the difference between those two values is that the region here is a bit smaller. That's all. So we still have regions here that can be able to explain the G minus 2 of the mu. And those red horizontal lines represent the 1 sigma bounds. For example, at the time, we have a value for the 1 sigma bound, which was this solid red line. And we had a projection for the 1 sigma line, which will basically means that the people at the time were projecting that the error of the measurement will be smaller. And so those two red lights, they're just for reference. That's all. And then we have these vertical lines. The first region here represents the limits, the current limits from LHC. So everything that are inside this region is excluded. And then we have the two projections. The first one for the high luminosity LHC, and the second one for high energy LHC. So everything that is inside those two regions perhaps can be a signal that can be seen at these two different upgrades of LHC. Okay. So let me talk now about the results. We did two different values for the mass of chi. Well, the first one we consider that the mass of phi, that the mass of phi was 10% of the value of the symmetry break of V chi. And the second one, we consider that it was 5% of V chi. As I said, this is a free parameter, so we can choose any value for this. And we consider those two because basically these are two cases where we can escape limits from LHC. And as you can see, as the dependence on the mass gets smaller, we get further from the limit from LHC. It's pretty interesting. And as you can see here, we have two different, well, the reason why we chose that is because we have two different regions. One of them can explain the G minus 2 of the muon, but it could induce a signal in high luminosity LHC. And the other one can explain the G minus 2 of the muon and induce a signal into high energy LHC. So with this model, we can induce a signal in those two different upgrades of LHC, which is pretty nice. And here to this plot on the right, it's a bit more complicated to explain because there's way more information here. So this plot here, we're considering, this is now a plot of the Yukawa coupling of the inert scalar with only muons, which is lambda 2, as a function of the scale of symmetry breaking. And just in the same case here, the vertical lines represent the limits from LHC, high luminosity LHC, and high energy LHC. However, we now have a third component here. We are now adding the limit coming from lepton flavor violation. So this whole region here coming from the blue to the green are the region that can explain the G minus 2 of the mu in this plot. And as you can see, the Yukawa coupling has a sizable region that can be used to do that. So, however, when we consider the limits from lepton flavor violation, we have a sizable chunk of this area excluded, which is represented by this hatched area here. So when we consider lepton flavor violation, even though we are considering we made that assumption that the non-diagonal terms of the Yukawa matrix are smaller than the diagonal terms, we still have a very sizable region that is excluded. So this means that our assumption at the beginning was right to think that. However, we can still explain the G minus 2 of the mu while escaping the limits from the LHC, which is great. It's great news. However, as you can see now, I believe you probably can see this now, this represents a problem. because depending on the choice of the Yukawa couplings, perhaps we cannot explain the G-2 of the muon. But what if we put some symmetry in the model that perhaps, well, this inert scalar only interact with muons. So then this complementarity is lost. And we can still have a region that can explain G-2 of the muon, but the model will lose this appeal of being able to survive the limits from lepton flavor violation. And in the second case, since we have another free parameter, we thought it was interesting to make two different plots for two different values of the mass of the exotic lepton. Here, the first one on the left is the case of the mass of 200 GeV, and the second one was the case of the mass being 400 GeV. And as you can see, the changes in the mass of ME made some sizable changes in the model. Where the first case here, we cannot explain G-2 in a high energy LHC, and the other case, even with high energy LHC, we cannot see this particle. It's pretty interesting. And in the second case, there is a whole region here that can explain G-2 and could be seen at even LHC right now. It could have been seen. It's pretty interesting. So we have this different model, but in the end, the conclusion is the same. With this model, we have some regions that can explain the G-2 of the muon. That's the main takeaway here. And however, when we consider the lepton flavor violation, these models suffer a lot more than the model of just the scalar triplet. As you can see, the region that is excluded is way higher. It's a way larger region that is excluded. So this means that this was also a very interesting feature that we found when we were working with this paper was in the model with exotic leptons, there was a tendency of the Yukawa couplings to be higher in order to explain the G-2 of the muon. And then when we consider the limits from lepton flavor violation, a major part of this area was just excluded. So this also shows us that the complementarity with lepton flavor violation, even though it's a good idea, it makes our model suffer a little bit. It's pretty nice actually, because we can see that our model is very interesting in this case, can explain these different things and still survive it, but it's not how can I say, it's not a model that is free from anything, right? And the more limits that we put in our model, the more refining it will get. So that's pretty nice. And just as the previous case, we can also have, we still have a region that can explain the G-2 of the muon. However, the Yukawa couplings that can be used to do that, the region is very smaller. And that's pretty interesting. So just to conclude, I hope I did not take too much of your time. In this work, we provide some simplified scenarios as an extension of the 331 models in order to explain the G-2 anomaly of the muon. And we also consider limits coming from collider bounds and the case of lepton flavor violation. However, as I just said, when we consider lepton flavor violation, this complementarity, it puts some pretty strong limits in our model. However, even though when we consider this model, we can still explain the G-2 of the muon, which is great news. However, this relationship of the Yukawa couplings, it needs to be taken with care, because depending on the choice of the Yukawa couplings, we may lose this complementarity and even lose the region that can explain the G-2 of the muon. And that's it. First, I have some acknowledgements of my funding agencies and supporting agencies. And that's all. Thanks.
Thank you, Álvaro. Very important, the funding agencies, right?
Yes.
Thank you very much for the very nice talk. I think it was very well explained. I like it a lot. So is there any questions from the public? Please raise your hand. Okay. In the meantime, I have just one question, only from curiosity, on the first plot that you showed with the inert scalar model. You tried for two different masses, so that worked. Okay. just by curiosity, did you try higher, because you said that at lower masses you go away from the LHC, high Lumi, etc. Did you try higher masses to see if you somehow got into the on the green region?
Well, yes, because we are actually was the first thing I did, because I got curious about that as well. Because since I've seen this pattern of going away to the LHC limits, I was curious if there was a region that perhaps
the other way around.
It is true. Yeah, it doesn't explain the G-2 at all. But I remember that I've looked at it, I guess it was 4 of VK. That was the last value that I looked, because the coupling constant had these limits from unitary, the stability of the potential and all of that. So, and even in that case, we still will be able to explain the G-2 to mu. And I was very surprised by that because I didn't expect it at all.
Yeah.
But that's a very interesting question.
Cool, nice. Is there any other question?
So I have one, Álvaro. Very nice talk. I was curious about how exactly did you put the bounds? What was the procedure that you followed there?
So yes, you mean the bounds from colliders or from lepton flame violation?
No, from colliders.
Okay, so let me go back a few slides here. So these were the limits that we consider, okay? We know LHC, it puts limits on the masses of the particles, since they have only access of knowing the energy of these particles that they are part of the collisions, okay? So the limits only go to the masses. And here from these slides, we know that there is a relationship between the masses and the scalar symmetry break. So we basically infer how these limits would be in the scalar symmetry breaking from the limits from LHC to the masses, which basically, well, let's ignore this part here. Basically, I inverted the function. That's all.
Okay, thank you. It's pretty simple.
Yeah, it's a very simple procedure.
Is there any other question? Yes, go ahead.
Yes. Can you go to these plots with the red lines, the horizontal red lines, and in the results?
This one?
Yes. Yes. What's the difference between the green horizontal lines and the red horizontal lines?
Yes. The red lines, basically, they just represent the 1 sigma bounds, which are the error bars. That's all. Just as a reference, because there was a projection that they would reduce the error bars. So we've shown these red lines just as a reference. There's no
reference.
Yeah, just for reference.
Okay.
Alvaro, and you mentioned that you don't have the G-2 result from 2021, but they would only make your green region
smaller. Yeah.
Smaller. Yes, that's it, right? Okay.
Yeah, that's the only. And actually, I was part of a talk a few months ago, and I made sure to see if our model will still survive, with these new results. And that's the main thing that happened. The region between those lines got smaller. That's all.
Okay, good, thanks. Is there any other question?
Yes. The last question, Álvaro. In view of the content, of the rich content of your model, there's no way to couple your fermions with the muon and with the triplet scalars in order to account for this anomaly?
Well, they are
you introduced this inert triplet in order to account for the anomaly, but there's no way to couple the other triplets that you have in order to account for this?
Yes, the other triplets, they are also coupled with this model. And that was another thing that we have found from the previous paper. Let me just go back here. This paper here, which was also from last year. And we basically found that the other triplets that develop a vacuum expectation value, they had the contribution was suppressed. So they were not able to produce a sizable enough contribution to the G-2 of the mu to explain the anomaly. So that's the main reason why we didn't consider all of them.
Okay. Okay, I see. Thank you for the presentation. Very nice.
Thank you.
Are there more questions to Álvaro? No? Okay, Bastian, just one question. What was the problem that you actually have to get into the Zoom meeting? Just for my record.
I just copied the number, the
ID number.
A number of ID number from Facebook into this Zoom web page, and I couldn't enter.
Okay, I'm going to check the number. Maybe it's wrong. Thanks for letting me know. Okay, so if there are no more questions, thanks to all for coming. And thanks again, Álvaro, for this very nice talk. Have a nice week, and hopefully we will see each other again next Thursday.
You as well.
Bye-bye. Thank you.